And this is an energetics approach to the paper tube challenge. Paper tube challenge is that if we have a paper tube, a tube with paper wrapped around it, probably toilet paper, with mass m and outer radius r and inner radius little r, with everything else being paper on the inside in this region, and we drop it such that we release it and allow it to roll and drop it from height h, or we simply drop it without it unrolling from height little h, that released at the same time, these two hit at the same place, and we'd like to find the ratio of big H over little h such that the fall times are equal. The falling times are the same. And it's possible to do this from dynamics, but we can also do it from energetics. And so we're going to say that this is going to be object 1, and this is going to be object 2, and all of these things that follow. And we're going to say that after falling, it's going to hit the ground. I guess we should say it's going to hit the ground at some velocity v1 or some velocity v2 when they hit the ground. Really, when they pass through the same point, maybe a little bit above the ground, just so there's some bounce and stuff. And while falling, or right before hitting, I guess, this is also going to have some angular speed omega 1. Of course, the guy simply dropped, doesn't have an angular speed. And we say, well, energetically, the one who is unrolling has total energy, mg capital H at the start, and right before hitting has kinetic energy only, which is 1/2 mv1 square plus 1/2 I omega square, omega 1 square, as opposed to the one who is simply dropped, which has mg little h and picks up only mv2 square. So we're going to use a couple of things. Let's define the factor k to be simply the rotational inertia over mr squared. Of course, the rotational inertia is kind of complicated and can be found differently, but whatever it is, we can certainly divide it by the equivalent angular ring of mass m. That just lets us simplify some of the writing a bit, because now this equation can be written as mg capital H is 1/2 mv1 squared plus 1/2 kmr squared omega 1 squared. And we remember, of course, as always, that this is unrolling smoothly, so we know that omega 1 is v1 over the radius. And that allows us to say mg capital H is 1/2 mv1 squared plus 1/2 kmr squared v1 over r quantity squared, which is 1/2 mv1 squared plus 1/2 kmv1 squared. And so now we can say, well, we can now get rid of the m's and have that gh is 1/2 v1 squared plus 1/2 kv1 squared, or 1/2 1 plus k v1 squared. And of course, from our blue equation over here, we can certainly find quickly enough that g little h is simply 1/2 v2 squared, having canceled out this mass right here. So we're left with these things, which we can say, as we move a little bit down, that the ratio big H over little h is now 1/2 1 plus k v1 squared over 1/2 v2 squared, or interestingly enough, 1 plus that factor k times the ratio of the squares of the velocities, which is not tremendously useful at the moment because we don't have that. But have no fear, it will be fine in a little bit. Then we can do kinematically, so let's give ourselves a little bit of room here. And we could say from kinematics, we could also say, all right, that for uniform acceleration from rest, the average speed is 1/2 the final speed, right? This is basically saying, if we say that if we have sort of a time versus velocity plot, that our constant acceleration guy does something like this, and the average of that would be the area, the rectangle with the same area, but that clearly happens when this part exactly balances that part, which means that this has to be 1/2 of the velocity. So that's a pretty well-known result from kinematics. And so we can go back here and say, well, each height is going to be the average value of the velocity times the time, because that's what the average velocity means, which in this case is going to be 1/2 of v1. And likewise, lowercase h is going to be the average velocity of object 2, which is going to be 1/2 v2 times t. And so putting these two things together, we can see that h over h is going to be just v1 over v2, which is also not useful because we still have v1 over v2, but now we have two connections, so we just have to put them together. So from energetics, we have that big H over little h is 1 plus k, all times the square of v1 over v2. And from kinematics, we have that big H over little h is just v1 over v2. So what we're going to do now is we're going to go through this and say, let's put these two things together to yield the equation that big H over little h is 1 plus k times big H over little h quantity squared. And for algebraic convenience, and not to carry lots of weird fractions, let's just for the moment define that ratio as the letter z, and that lets me say that z equals 1 plus k times z squared. So then we can bring this over and say that 1 plus k times z squared minus z equals 0. So z times 1 plus k times z minus 1 all equals 0. When two things multiply to 0, such as this or this, it means that one or both are 0. So either z equals 0, which is weird, but if we drop them from 0 height, then I guess they hit the floor at the same time, so that's technically a solution. Or 1 plus k times z equals minus 1 equals 0. So 1 plus k times z equals 1, or z equals 1 over 1 plus k, which ultimately goes back to saying that big H over little h is 1 over 1 plus k, which conveniently agrees with the answer from dynamics, so we're in good shape here.